Snowboarding can be an intensive sport, not only for the riders but for their boards as well. In high-level competitions, the characteristics of a board must be just right. For example, in downhill competitions, riders require stiffer boards which allow them to read higher top speeds, whereas in trick-based competitions, like the halfpipe, riders require their boards to be more flexible, as flexible boards allow for finer control of movement. The goal of our project is to experimentally find the bending characteristics of a prototype board in action. Characterizing the bending of a board could be a useful component in future design iterations. Such data could also be useful if used in conjunction with other telemetry data used in modeling the dynamics of a rider. With our project, we found many challenges that need to be addressed while attempting to measure the bending characteristics of a board in action. The first challenge would be accidentally shorting out the circuit from snow getting inside the strain gauges. A simple solution to this challenge would be a waterproof casing, like epoxy or an insulated case. Both these options provide protection against the harsh environment and the moisture put on the board in order to provide an accurate strain measurement. The next challenge that we found is the strain gauges would only measure strain on the surface of the board, neglecting internal strain. For this project, we would like to measure both internal and external strain. One solution we thought of would be to embed the strain gauge into the board. This would provide us with both internal and external data. Next, we found that the influence of temperature fluctuations on a strain gauge measurement could be an issue. However, as discussed in lab, using a Wheatstone bridge with a dummy gauge could minimize these temperature fluctuations and ensure accurate data. The fourth challenge we faced would be the actual data acquisition system and its lack of portability for the live test run. The most obvious solution would be to go wireless and eliminate the need for the system to be on the rider. However, as this could get expensive, a much smaller portable data acquisition system, able to be held by the rider during the run, is a feasible option. Wireless is definitely preferred, though. The last challenge would be fear of overloading the strain gauge. Since the forces can be small to very large, we would need a strain gauge with an ample range in order to capture all of the data. An example of this would be from 30 ohms to 3 kiloohms. Now, while all of these challenges exist and are there, luckily they all have solutions that can be implemented to ensure accurate and precise data. The implementation of strain gauges to the prototype of a snowboard in action can pose a couple of safety implications. If the data that is collected from the application is wrong, this can be an issue if that data is applied to future prototype designs. The implementation of this data could result in the snowboard design failing during use, which can cause serious injury or even death to the person riding the snowboard. To avoid this, it is recommended to have a large factor of safety to not risk the occurrence of any incidents. Additionally, having a large factor of safety is important for the products designed for use in difficult environmental conditions. To properly measure the loads on a board, strain gauges need to be able to measure torsional and longitudinal bending. To measure these strains, we would use the strain gauge setup as outlined by researchers in the article Laboratory, Computational, and Field Studies of Snowboard Dynamics. According to their setup, there should be a total of 6 strain gauges. This can be seen in the picture below on this slide. 2 strain gauges will be positioned on either end of the snowboard along the center line. This placement will enable us to measure the bending strains at the tip, center, and tail of the board. The remaining 4 strain gauges are to be placed on the edges of the board in a rectangular configuration. Once again, this can be seen on the same picture. This will allow for the measurement of the strain on the board while it is in torsion or when the rider is riding on one edge. Due to the harsh snowy environment, the strain gauges will require protection from electrical failure due to moisture and any physical damage caused by the rough terrain. This was brought up earlier in our challenges section of the PowerPoint. To mitigate the effects of moisture and physical damage, the strain gauges should have a durable waterproof casing, such as epoxy or rubber. Furthermore, the gauges could be better protected by embedding the gauges into the board or placing them on top of the board. However, the placement of the gauges relative to the depth on the board would change the type of load the gauge would experience, compressional or tensile. Once again, this was brought up with our internal versus external measurement in the challenge section of our PowerPoint. We cannot say how the change in load type would affect the output of our strain gauges, but it is definitely something to consider with placement of the strain gauges. For our application, data collection would ideally be conducted through a data collection system that would wirelessly capture and transmit the data in real time to a separate computer where the data would then be displayed. This way, the data from the strain gauges would be transmitted to a computer on the ground while the rider is conducting the live tests. This method would prevent the hindrance of the rider having to strap a data acquisition system on their person while they're snowboarding. However, an alternate method of gathering data could be to have the strain gauges directly wired to a data acquisition system and have that data stored there. The rider would then have to carry the data acquisition system on their person while they conducted the live test. One thing that should be considered with this alternate method is that the presence of wires might affect the way the snowboarder rides, which in turn could affect the type of data that the data acquisition collects. Once again, this was mentioned earlier in our challenge section of the presentation. For our application, a voltage measurement is the desired output. The reason for selecting a voltage measurement over a resistance measurement stems from the fact that a resistance measurement would be to our disadvantage. This is because it's subject to extreme fluctuations under temperature changes. Additionally, because a change in the resistance of a strain gauge is very small, a sensitive measuring device would be required. Sensitive measuring devices tend to be more delicate, which is not optimal for high-impact applications, like snowboarding. On the other hand, a voltage measurement would not require such a high-precision measuring device. Likewise, a voltage measurement would prove to be more advantageous because although voltage is still affected by temperature fluctuations, this effect is counteracted by the incorporation of a Wheatstone bridge with a dummy gauge into the setup. Based upon where strain gauges are placed on the board, we want our system to have output units of force, in either foot-pounds or newtons, to measure the longitudinal bending of the board. And we want our torque units to be foot-pounds or newton-meters to measure the torsional bending of the board. To calibrate the strain gauges, the gauges will first be mounted on the board and then known forces will be applied. The voltage outputs of the gauges can then be plotted against the known forces. This plot will be used to create a trend line. Using the trend line data and the residuals, we can calculate the uncertainty of the calculated forces from the trend line. Using the calibration results, we will have an estimate of output resolution and a good estimate of incoming unknown forces. Thanks for listening from Team 7.